November 14th, 2023. A spacecraft that had already left our entire solar system suddenly went silent, on sending back nothing but a meaningless stream of garbled binary code. For months, the engineers responsible for it genuinely feared it was lost forever, gone for good after nearly half a century of operation. The spacecraft was Voyager 1, and the cause of that unsettling silence turned out to be a memory failure inside its onboard flight data system, a fault that risked permanently cutting off communication with the most distant human-made object ever built. The team refused to give up. They made a genuinely bold call, reallocating the corrupted code to a completely different section of the probe's aging memory, a fix that began on April 18th, 2024. With every single step of it a leap into the unknown, since a signal sent from Earth takes roughly 22 and a half hours just to reach Voyager, and another 22 and a half hours for any reply to travel back. Just 2 days later, after months of intense, anxious work, something incredible happened. Voyager 1 re-established contact with Earth. So what exactly did this remarkable spacecraft discover out at the true boundary of our solar system, and why did that boundary turn out to look nothing like scientists originally expected? Most people picture the edge of the solar system as some kind of gentle fade into empty darkness, a slow, boring transition with nothing much to report. The two Voyager probes proved that assumption spectacularly wrong, uncovering sharp boundaries, mysterious sounds, unexplained density spikes, and an entire hidden bubble of space that scientists did not even know existed until fairly recently. To understand why this all matters so much, it helps to go back to the beginning. In the late 1970s, a rare planetary alignment occurred, one that only happens once every 175 years, with the outer gas giants lining up in a way that made it possible to visit several of them in a single mission. NASA seized that narrow window, launching both Voyager probes just weeks apart in 1977. Voyager 1 eventually overtook its twin thanks to a faster trajectory, and just 13 days after launch, it captured a now famous photograph of Earth and the Moon together from millions of miles away, a fitting symbol for the start of an extraordinary journey. Nobody involved in that mission could have possibly guessed just how far these two small nuclear-powered spacecraft would eventually travel, or how many decades they would keep operating well past their original expiration date. By 1979, both probes had reached Jupiter, revealing rings nobody knew existed, discovering new moons, and confirming that Ganymede, not Titan, is actually the largest moon in the entire solar system. They also found that Europa's surface was covered in smooth ice riddled with deep cracks, data that eventually led scientists to suspect a hidden ocean lying beneath that frozen shell. From Jupiter, both probes used a gravity-assisted slingshot to reach Saturn by 1980 and 1981, delivering our first truly detailed look at its intricate rings, and discovering that Saturn's largest moon, Titan, had a thick, hazy atmosphere hiding its surface completely from view. At Saturn, the two spacecraft's paths diverged forever. Voyager 1 was deliberately steered close to Titan to study that mysterious atmosphere, a decision that sacrificed any chance of continuing on to the other outer planets, while Voyager 2 pressed onward toward Uranus and eventually Neptune. Voyager 2 reached Uranus in January of 1986, and scientists were genuinely surprised by what they found, an entirely different kind of planet compared to Jupiter and Saturn. Where true gas giants are roughly 90% hydrogen and helium all the way through, Uranus only carries those elements in its outer atmosphere, hiding an ocean of water, ammonia, and methane underneath, wrapped around a solid core of rock and ice. Planets built this way eventually earned their own category, ice giants, and Uranus turned out to be the coldest planet in the entire solar system, even colder than Neptune, despite sitting much closer to the Sun. Everything humanity currently knows about Neptune up close, its faint rings, its violent storms, its icy moon Triton, all traces back to that single brief flyby nearly 4 decades ago, since no follow-up mission has ever managed to make the return trip. It captured our first detailed images of a planet that appeared vividly blue at the time, though later analysis revealed its true color leans closer to a deep teal. Meanwhile, Voyager 1, its own planetary tour finished after Saturn, had most of its remaining instruments deliberately powered down to conserve energy, keeping only what it needed to study the surrounding environment. But in February of 1990, from a staggering distance of nearly 4 billion kilometers, it turned its camera back toward home one final time, and captured Earth as a tiny, barely visible speck of light. What followed was a long, quiet stretch lasting well over a decade, interrupted by something extraordinary in August of 2012, when Voyager 1's instruments recorded a sharp, sudden drop in charged particles streaming from the Sun, paired with a corresponding spike in particles arriving from deep interstellar space. That combination meant only one thing. Voyager 1 had finally crossed out of our solar system's protective bubble entirely, becoming the first human-made object to reach true interstellar space. Its slower-moving twin, Voyager 2, crossed that same boundary in November of 2018. This protective bubble, called the heliosphere, stretches roughly 18 billion kilometers out from the Sun in every direction, shaped by the constant outward pressure of the solar wind, a steady stream of charged particles flowing off the Sun's surface. The outer edge of that bubble is called the heliopause, and it marks the true dividing line between our solar system's influence and the vast interstellar medium beyond. And what both Voyagers found, once they crossed that line, genuinely upended existing theory. Scientists had long assumed the solar wind would simply fade out gradually the farther it traveled from the Sun. Instead, the data showed something far stranger. The solar wind does not fade away at all. It slams into a surprisingly sharp boundary and essentially stops there, redirected rather than dissolved. On the inside of that boundary, solar plasma flows around the heliopause, while interstellar plasma flows around it from the outside, forming an actual physical wall between two completely different environments, rather than a gentle, gradual transition. Even stranger, this boundary is not fixed in place. The surface of the heliosphere is constantly warped by enormous, unpredictable waves, distortions that can stretch out across roughly 10 times the distance between the Earth and the Sun. Studying the data closely, scientists also discovered that the heliopause itself shifts and changes shape surprisingly quickly, which may help explain why it took a full 6 years longer for Voyager 2 to cross that same boundary compared to Voyager 1, even though both were traveling in roughly similar directions. These rapid shape changes still do not fit cleanly into existing scientific models and remain genuinely unexplained to this day. The temperature and density readings near that boundary threw up their own puzzle, too. Physicists had expected solar particles slowing down as they collided with interstellar radiation to produce a sharp spike in both temperature and density right at the boundary. That spike did happen, but the measured values came in roughly 10 times lower than theoretical predictions suggested they should be, and exactly where that missing energy went remains an open mystery. Even after years of additional analysis, nobody has come up with a fully satisfying answer for where that expected burst of thermal energy actually disappeared to, and it remains one of the more frustrating unsolved puzzles tied directly to this entire region of space. Data from both spacecraft also revealed that interstellar space itself is filled with denser, colder plasma, while the plasma, sitting just inside our solar system's boundary, runs hotter and noticeably thinner. Crucially, these two very different types of plasma do not simply sit side by side, ignoring each other. Particles from the solar wind and particles from interstellar space actively mix together, forming a genuine boundary layer sandwiched between the heliopause and true interstellar territory. Not unlike two ocean currents of very different temperature meeting along a coastline, neither one instantly overwhelming the other, but blending together gradually along a churning, turbulent seam. On top of that, shock waves generated by the Sun itself have been detected passing straight through the heliopause and rippling out into interstellar space, creating disturbances not unlike the shock waves produced by an exploding star. Proof that its influence stretches meaningfully further than the visible boundary of the heliosphere itself. Thanks to this data, scientists also learned that the interstellar magnetic field out there is 2 to 3 times stronger than anyone had previously calculated, which in turn means interstellar particles are pressing against our solar system's protective bubble with roughly 10 times more force than earlier models predicted. That single revised number alone forced researchers to redraw parts of their models for how our solar system's bubble holds its shape against the pressure of the surrounding galaxy. All of this combined data gives researchers a far more complete picture of exactly what happens, where our sun's influence finally gives way to the wider galaxy. Insights that scientists believe likely apply to countless other star systems scattered across the Milky Way as well. Since every star out there pushes its own version of a solar wind outward, carving its own protective bubble through the surrounding interstellar medium. Throughout their long journey across interstellar space, both Voyager probes have kept transmitting steady updates on their instruments and their location back to Earth. But in 2012, while sitting roughly 23 billion kilometers from home, Voyager 1 unexpectedly began transmitting a genuinely strange signal, a chaotic stream of data about its own position that repeatedly cycled through sequences of zeros, or the number 377 over and over again. This mysterious signal briefly puzzled engineers, since that kind of repeating numerical pattern could theoretically have signaled either critical new information or serious malfunction. It turned out to be the latter, an issue traced back to the spacecraft's attitude control and maneuvering system, which had apparently lost precise awareness of its own orientation in space, likely due to cosmic radiation quietly interfering with its aging navigation hardware. Engineers back on Earth resolved the problem by rerouting telemetry data through an entirely different onboard computer, a genuinely elegant fix for a spacecraft that far from home, essentially routing around a damaged section of hardware, the same way a driver might take a detour around a closed road without ever being able to physically inspect the damage firsthand. Then came that far more serious communication blackout starting in November of 2023, caused this time by corrupted code sitting on one of Voyager 1's onboard chips, ultimately resolved through that careful memory reallocation process completed in April of 2024. These repeated near misses are a genuine reminder that both spacecraft are approaching the very end of their operational lives. NASA hopes their remaining scientific instruments will keep functioning for at least a few more years before a phased shutdown eventually begins, likely somewhere close to the 50th anniversary of the entire mission, at which point both probes will simply lose the power needed to communicate with Earth ever again. Even after that final silence, though, both spacecraft will keep drifting onward through deep space indefinitely, potentially witnessing genuinely fascinating cosmic events that we will simply never learn about, since they will no longer have any way to tell us. Right now, Voyager 1 is roughly 24 billion kilometers from Earth, moving away at a steady pace of about 3.5 astronomical units every year, heading generally toward the constellation Camelopardalis. In the distant future, around the year 4272, it will pass within roughly 1.7 light years of an obscure little-known star sitting in the constellation Ursa Minor. Voyager 2, meanwhile, sits about 20 billion kilometers from Earth, moving slightly slower, and in roughly 40,000 years, it will pass within about the same distance of a small star called Ross 248, located in the constellation Andromeda. Interestingly, even though both probes crossed the heliopause years ago, it is not entirely accurate to say they have truly left the solar system altogether. Scientists generally define the true boundary of our solar system as the outer limit of the sun's gravitational influence, and the current leading candidate for that ultimate edge is a hypothetical, mostly unconfirmed region called the Oort cloud. Believed to be the true source of long-period comets that occasionally swing in toward the inner solar system, this region is thought to include two distinct parts: an inner disk-shaped zone and a much larger, roughly spherical outer shell, with that outer edge estimated to sit somewhere between 50,000 and 100,000 astronomical units from the Sun. At Voyager 1's current speed, it would take roughly another 300 years just to reach the inner edge of that theoretical cloud, and possibly another 30,000 years beyond that to fully cross through it, which would mark its actual final departure from the solar system in the fullest sense. Put simply, everything we usually picture as leaving the solar system, crossing the heliopause, entering interstellar space, is really only the first true boundary, not the final one, and both Voyager probes still have an almost unimaginably long road ahead of them before they can genuinely claim to have left the sun's gravitational grip behind entirely. Both spacecraft carry something else worth mentioning too, a golden phonograph record mounted on the outside of each probe, containing photographs, greetings recorded in dozens of different languages, natural sounds from Earth, and roughly 90 minutes of music, all included in case either probe is ever discovered by some future intelligence out there among the stars. Whether or not that ever happens, both Voyagers will simply keep drifting quietly through the cold, dark void of interstellar space indefinitely, standing as a lasting symbol of humanity's genuine curiosity about what lies beyond our own small corner of the universe. Whether any distant civilization ever actually finds one of these golden records is anyone's guess, but the fact that we bothered sending one at all says something meaningful about how humans choose to introduce themselves, not with weapons or warnings, but with music, photographs, and greetings spoken in dozens of different languages. Now here's where things get genuinely strange, because the boundary of our solar system was not the only bizarre discovery tied to these two spacecraft. As both probes moved further and further from the sun, they picked up something that made almost no sense at first. The density of space around them started increasing the farther out they traveled. Interstellar space is often casually described as an empty vacuum, but that is not quite accurate. Matter out there is extraordinarily sparse, but it is not entirely absent. Near the sun, the solar wind typically carries somewhere between 3 and 10 charged particles per cubic centimeter, a number that naturally drops the farther you travel from the sun, reaching its lowest point right at the heliopause boundary, where the density of particles falls to a tiny fraction of a particle per cubic centimeter. Based on existing calculations, scientists expected the density just beyond that boundary, out in true interstellar space, to rise only modestly. When Voyager 2 actually measured this at a distance of roughly 18 billion kilometers from the Sun, the reading came back remarkably close to the prediction. But at a slightly greater distance, the density had climbed far higher than any existing model predicted, and scientists still do not have a fully satisfying explanation for exactly why that density keeps climbing the way it does. It is a genuinely strange result, since intuitively you would expect space to simply keep thinning out the farther a spacecraft travels from any star, not gradually pack itself with more particles, the deeper it pushes into supposedly empty interstellar territory. While we're on the subject of unexpected bubbles, it turns out our entire solar system sits inside something even larger and stranger than the heliosphere itself. Deep space images often give the impression of thick clouds of interstellar dust and glowing gas scattered everywhere. But starting back in the 1970s and 1980s, astronomers began noticing that the region of the galaxy immediately surrounding our own sun looked strangely empty by comparison. More recently, researchers at the Harvard-Smithsonian Center for Astrophysics confirmed exactly that using an extraordinarily detailed three-dimensional computer reconstruction of the surrounding galactic neighborhood, showing that the Sun and Earth sit almost dead center inside a genuinely enormous cavity roughly 1,000 light-years across, which researchers have named the local bubble. According to their calculations, this bubble likely began forming around 14 million years ago, carved out by a rapid series of roughly 15 separate supernova explosions occurring over the span of several million years. That chain of explosions pushed surrounding interstellar gas outward with tremendous force, creating a hollow, bubble-shaped cavity with a dense outer shell. And remarkably, that bubble is still expanding today, currently growing outward at a slow but steady pace. Along the dense surface of this bubble, researchers identified at least 7 distinct regions of active star formation, dense pockets of molecular gas, where entirely new stars are actively being born right now, suggesting the same process is likely playing out on the surface of countless similar bubbles scattered elsewhere across our galaxy, some of which may well contain their own stars with their own planets, quietly sitting inside their own local bubbles just as we are. It is a strange thought that somewhere out there, another civilization might be looking up at their own unusually clear night sky, entirely unaware that the reason they can see so far into the cosmos is the exact same coincidence of geography that lets us do it here on Earth. Interestingly, our own sun was not originally anywhere near the center of this bubble when it first began forming. At the time those ancient supernovae exploded, the sun was actually sitting roughly 1,000 light-years away from the entire event. It was only as the sun continued its own long orbit around the center of the Milky Way over the course of roughly 5 million years that it eventually drifted almost perfectly into the middle of the expanding bubble, a coincidence supported by traces of radioactive isotopes tied to ancient supernova activity found embedded in layers of Earth's own crust. Researchers involved in this discovery have pointed out that, statistically speaking, our sun would be extremely unlikely to sit near the center of one single giant bubble, unless bubbles like this one are actually fairly common throughout the galaxy, meaning our sun has very likely drifted through several similar bubbles over the course of its long history and simply happens to currently be sitting inside this particular one. Researchers have described the wider galaxy almost like a piece of Swiss cheese, with each hollow pocket carved out by past supernova explosions and fresh stars continually forming along the dense edges of those very same holes. With this bubble mapped out, the fuller structure of our solar system finally comes into focus. At the very center sits the Sun, with 8 planets orbiting around it, the outermost being Neptune, sitting roughly 30 astronomical units away, meaning 30 times farther from the Sun than Earth itself. Beyond Neptune lies the Kuiper Belt, a broad collection of small icy bodies, including the dwarf planet Pluto, stretching out to roughly 55 astronomical units. Further still, somewhere between 125 and 135 astronomical units out, sits the heliopause itself, that sharp, turbulent boundary where solar plasma collides head-on with interstellar plasma, essentially a cosmic traffic jam, where particles pile up against each other at incredible speed. Beyond that collision zone, somewhere around 3/4 of a light year to a full light year and a half out, the theoretical Oort cloud begins, a truly enormous spherical shell potentially containing up to 1 trillion icy objects, the ultimate source of those unpredictable long-period comets that occasionally swing in toward the inner solar system, after millions of years of drifting undisturbed. You might reasonably ask why any of this actually matters for life here on Earth. As it turns out, the heliosphere itself plays a genuinely important protective role, effectively shielding our entire solar system from a constant barrage of high-energy cosmic particles streaming in from deeper regions of the galaxy. As for the much larger local bubble surrounding it, astronomers have separately determined that our galaxy, the Milky Way, is shaped like a broad spiral disk with several distinct arms extending outward from its center. Our Sun currently sits roughly halfway between 2 of those spiral arms, completing one full orbit around the galactic center only once every 200 million years, a span scientists refer to as a single galactic year. In that context, only a tiny fraction of one single galactic year has passed since modern humans first appeared on Earth. Over the course of its much longer orbit, though, the Sun has repeatedly passed through regions of significantly denser interstellar gas, including the crowded spiral arms themselves, where matter density can spike hundreds of times higher than what we experience today. Some researchers studying detailed models of the Milky Way have found a striking correlation between those past crossings through denser spiral arms and several of Earth's known mass extinction events, spaced out across hundreds of millions of years of geological history. That pattern suggests our Sun may currently be sitting in an unusually quiet, favorable stretch of its orbit, coinciding suspiciously well with the timeline of human civilization actually emerging on Earth in the first place. Whether that is pure coincidence or something more deeply connected remains an open question science has not yet fully answered. Beyond these two enormous cosmic mysteries, Voyager 1 delivered one more genuinely eerie discovery, a strange, steady hum detected far beyond 14 billion miles from Earth. This particular signal held remarkably steady at roughly 3 kilohertz for nearly 3 full years, making it one of the most stable, long-lasting signals the spacecraft has ever picked up, only detectable once Voyager 1 had traveled far enough away from the noisy interference of our own solar system. Most scientists believe this hum comes from plasma waves rippling through the surrounding interstellar medium, since plasma makes up much of the raw material found throughout deep space. What genuinely surprised researchers, though, was just how consistent that signal remained even after the spacecraft traveled another full billion miles further out, a level of stability that has left some scientists wondering whether some unidentified, ongoing dynamic out there might be responsible. Sound itself cannot travel through the vacuum of space the way it does here on Earth, since there simply are not enough particles out there to carry those vibrations. But electromagnetic and plasma waves travel through that near vacuum just fine. And while human ears cannot naturally perceive them, scientists have learned to convert these signals into audible sound, which is exactly how we are able to listen to this strange, distant hum at all. Closer to home, NASA has also picked up a handful of other strange, unexplained sounds within our own solar system, including an oddly haunting signal recorded near Jupiter's moon Ganymede, later linked to naturally occurring electromagnetic waves that also happen to produce auroras, similar to the ones we see here on Earth, as well as around Saturn and Jupiter. Even NASA's Perseverance rover, quietly rolling across the surface of Mars, has picked up an unexplained high-pitched scratching sound alongside the ordinary noise of its metal wheels crunching over rocky terrain, a sound that, to this day, nobody has fully explained. NASA engineers have run through the usual suspects: thermal expansion of metal components, small pebbles caught in the wheel mechanism, dust interference, but none of the standard explanations have fully accounted for the specific pattern of the noise, leaving it filed away as one more small, unresolved oddity from a planet that keeps surprising us. Looking ahead, scientists have already begun discussing a possible new interstellar probe mission sometime around 2030, one designed to travel roughly 10 times farther than Voyager 1 ever managed, potentially marking humanity's next truly significant leap toward the stars. In the entire history of spaceflight, only 5 human-made spacecraft have ever gathered enough momentum to leave our solar system behind entirely, and the 2 Voyager probes remain by far the most productive and longest-lived of that small, remarkable group, already operating decades beyond their original planned lifespan. Officially approved back in 1972 under an entirely different working name, both spacecraft eventually launched in the late summer of 1977, packed with dual redundant onboard computers, each carrying a strikingly small amount of memory by modern standards, barely enough to store a single average-sized photo taken on a smartphone today. And yet, using nothing but that modest, decades-old hardware, these 2 aging spacecraft have already rewritten our understanding of the outer solar system multiple times over. As long as they keep sending back even the faintest whisper of a signal, there is a very real chance they still have a few more genuine surprises left to share with us before they finally fall silent for good. Every single time engineers back on Earth have written off one of these spacecraft as finally reaching the end of the line, some clever software patch, some overlooked backup system, some careful bit of remote troubleshooting has managed to squeeze out a few more years of operation. And honestly, betting against Voyager at this point feels like a losing bet, given just how many times these 2 probes have already defied their own official expiration date. When the mission was first approved back in 1972, nobody involved expected either spacecraft to still be functioning, let alone making new discoveries more than 5 decades later, drifting through a region of space nobody had ever directly sampled before. The computers on board are almost laughably primitive by today's standards, executing a tiny fraction of the instructions per second that a modern smartphone handles without even noticing the workload. And yet that same primitive hardware, carefully rationed and maintained across billions of kilometers of empty space, is precisely what delivered every discovery covered here. Proof that the edge of our solar system was never the quiet, empty place anyone expected it to be.